Looking at the properties of discontinuity. The properties of limits also hold true for continuity. The properties of limits also hold true for continuity. Meaning if f and g are continuous functions at C, then f plus g is continuous at C. In other words, the sum is also continuous. F minus g is continuous at C. The difference is continuous. F times g is also continuous at C. And then some constant times f is also continuous. And finally, the composition f big circle g is continuous. So just like limits, it's also the same for continuity. So you have to be mindful of these things. So let's say you had a question like this. All right, so find the interval of continuity of this function. You can look at it individually. Okay, so since sign of something, this is a listening check, underline the word find. Underline the word find. Since sign of something is continuous, because sign is a continuous function, and also y equals x plus 2 is a linear function, so that's continuous. Since those things are both continuous, then the combination of both of them, so then sine of x plus 2 is also continuous because of the composition property. Alright, furthermore, y equals x, so the x by the sine, we know that's a linear function, that's continuous. So when you multiply that by sine x plus 2, which is already continuous, then the result is it's also continuous by the product property. Now if you look at y equals 1 over absolute value of x, that's continuous everywhere but at 0, because remember the denominator cannot be 0. Continuous everywhere but at 0. So this whole function, the function f of x, is continuous on all real numbers except when x equals 0, because it's undefined at that point. And we can rewrite it for short. This is what you write it, correct set notation for it. So let's take a look at some examples of that. Let's say we had this function. What you do is you look at it individually. So y equals x, all real numbers, is continuous everywhere. And then look at x plus 3, the radical sine x plus 3. Well, no, it has to be greater than or equal to 0. So solve for x, and you're going to get x is greater than negative 3. Now you're going to combine them together and then say when it's continuous. So the first one's everything, the second one just numbers bigger or equal to 3, so the set notation would be close bracket, because it's including negative 3, to infinity when you put both of them together. So that's the continuity interval. This is a listening check. Color in continuous at and the interval. Color in continuous at and the interval. Let's take a look at another example. Say we have this function. And I'm going to write down the notes so that you know how to do it no matter what the function is. So number 1, break it down to individual functions. Number 2, determine continuity of those individual functions. Number 3, combine all the restrictions. Alright, so breaking this down, I'm going to break it down to x plus 1. I'm going to break it down to the square root of x, and I'm going to break it down to 1 over x. So the function, the linear function, that's all real numbers. It's continuous everywhere. This one's continuous for numbers that are bigger or equal to 0, because the square root of 0 is 0. It's defined. So it's continuous on there. This one is continuous everywhere but when x is equal to 0. Now combine all those restrictions to get your interval. So it's everything greater or equal to 0, but because it can't be equal to 0 on the last one, it's everything greater than 0. So open circle, starting at 0, and it's all numbers bigger than 0. So open circle at 0 going to infinity. Open circle because infinity is not a number. Alright, the other way they can ask you this question is to find missing things or items in the question. So find a constant a or constants a and b such that the function is continuous on the entire real line. This is a listening check. Underline real line. Underline real line. And again, as long as you know the three things that make a function continuous, that is, f of a is defined, the limit as x goes towards a of f of x exists, and that f of a is equal to that limit, then the function is continuous. So let's take a look at each of those individual things. So the first one, f of a is defined. So you look at the endpoint, so you're looking at 1. Is f of 1 defined? So you plug in 1 where it's equal is the first one, so 3x squared. So you're going to get 3 times 1 squared, which is 3. Yes, it's defined. Perfect. So far so good. The limit as x goes to 1 of the function, so from the left, from the right, and if those two things are equal, then the limit exists as it goes to 1. So let's take a look from the left. From the left, so the point is 1. From the left of 1 would be 0. So it's any number less than 1. So that's this function here. So write that out. From the right, it's going to be numbers bigger than 1. So then that function would be 3x squared. Write that down. And in order for them to be equal to one another, that's the only way the limit's going to exist. So I know ax minus 4 must be equal to 3x squared. Well, let's take a look at what happens as x goes to 1. So plug in 1 where you see x. Evaluate it, so you're going to get a minus 4 equals 3. Solve for a, so a is 7. So if a is 7, 7 times 1 is 7 minus 4 is 3. So the limit as x goes to 1 of fx is 3. And finally, where the function is defined is equal to the limit. Let's take a look at one more example. Let's make this one a little bit more complicated, where you have a system of equations. If you don't know how to solve systems of equations, there's actually a video on it. Just ask me and I'll direct you towards it. Alright, so again, in order for a function to be continuous, it must be defined at those points. So the endpoints here are -1 and 3. So let's make sure that it's defined at f is equal to -1 and f is equal to 3. So you're just going to plug it in. So when f is equal to -1, the function is equal to 2. When x is equal to 3, when the function is equal to 3, that's going to be -2. So it's defined, that's good. Alright, perfect. Let's take a look at the limit. Does the limit exist? Which means you need to take a look at x going to -1 and as x goes to 3. Both from the left and from the right. So I'm kind of just organizing it a little different. From the left and from the right. And if they're equal to one another, the limit exists. So from the left of -1 would be like -2 and so forth. So that means that it has to be numbers less than -1, which means it's 2. So the limit is equal to 2. From the right would have to be numbers bigger than -1, which would mean that it would be ax plus b, which I don't know what ax plus b is, but when I plug in -1 as the limit as it goes to -1, I'm going to get -a plus b. So that's equal to 2. That's one equation. I'm going to do the same thing for when x is equal to 3. So from the left, a number is left of 3, which means I go with the first one, ax plus b, and it's the limit as x goes to 3, so I put 3 where x is, I get 3a plus b. And then from the right is numbers bigger than 3, and so when numbers are bigger than 3, it's equal to -2. So now I have those two equations, and I'm going to solve this using the system of equations. If you don't know what that is, again, ask me and I'll direct you to the video. So I'm just going to line it up, a's with a's, b's with b's, numbers with numbers, these two things. Right? Then what I'm going to do is I notice that the b's already have the same coefficient, so if I subtract these two, I'll get -4a, and watch what happens to b, they disappear. then I'll get 4 over there. And look, if I solve for a, I'm going to get -1. Now take that in and plug it into the first one. So negative of -1 plus b is equal to 2. So +1 plus b equals 2, so b is equal to 1. So that's using systems of equation. You can plug it back in to make sure that the limit does exist. So when I plug in -1 for a and 1 for b, I'm going to get -3 plus 1, which is -2. And over here, +1 plus 1 is +2. So the limit does exist. And you can see that they're equal to one another. So that works. And that's all it is. So let's practice.